All right. Welcome everyone to the afternoon session of the 18th annual workshop of CHAM++ and applications. The keynote speech that begins this session is from someone whom we have been waiting to hear from for a while as well. So I'm very happy to welcome John Mellor-Crummey, professor of computer science and electrical engineering and computer science at Rice University. All of us know him because of his association also with HPCToolkit. He's been leading that project for many years now. Probably not as many years as we have been doing CHAM++, but maybe close. So, and it's a very successful project. It's being used in the ECP project as well. So prior to ECP project, it was being used all along. It's not just designed for that, but ECP project is playing a big role. And the exascale machines, as we know, are pretty complex and large. And to do the performance analysis for those would be a challenging task. I also knew of John's work on debugging and race conditions. That's one of the interesting things from early on that I remember. I think in connection with that, he has this Dijkstra prize that he received. He's also an ACM fellow. And without getting in a long description, I would let him talk. So, John.
Thank you, Sanjay. I'm glad to join you for the workshop. The timing could have been a little bit better for me. As it turns out, there's a concurrent exascale workshop at Argonne that I'm trying to also attend. So I've been sort of in and out for various sessions for this workshop. I got to hear Jeff's keynote yesterday. So Jeff was talking about the long-term future of heterogeneous applications. I'm going to talk about something that's a little bit closer to term, which is the forthcoming DOE exascale supercomputers. And so, as many of you know, all of the forthcoming DOE exascale supercomputers are GPU accelerated. There's Aurora at Argonne that's based on Intel Xeon processors and forthcoming Intel Z Ponte Vecchio GPUs. There's an AMD-based system going in at Oak Ridge, and it has AMD Radeon GPUs. And then finally, the El Capitan system that's supposed to be installed by Livermore in around 2022 is supposed to have next generation AMD CPUs and AMD GPUs. And so with all of these GPU accelerated systems, over 95% of the flops come from the GPUs, and so it's very important to be able to use the GPUs effectively. So as Jeff was describing yesterday, there's a variety of programming models for these forthcoming exascale systems at the node level. So they're the native programming models that are available from the platform vendors. There's Intel's DPC++, which is extensions to the SYCL specification developed by Khronos. And there's AMD's HIP, which is a CUDA-like model. Finally, there's the directive-based models, the OpenACC model, which has been used for quite a few years for writing applications for the Titan supercomputer. OpenMP is being extended with offloading to support offloading parallel regions and loops to GPUs. And then last, there's a set of template-based programming models that are being developed in the DOE. Lawrence Livermore's Raja programming model and Sandia's Cocos model, which are intended as abstraction layers to support portability. So an application developer can write their code using either Raja or Cocos templates, and then the templates can be instantiated with whatever underlying programming layer makes the most sense for achieving the best performance on a particular target platform. So these are the node level models. Now at a higher level, there's a diverse set of global programming models. There's the message passing interface, of course. There's also partition global address space programming models. and the object-based Charm++ programming model. And these are not just my own musings. This is actually something that came from the Frontier specification sheet. And so they're actually expecting these models to be used on these large-scale systems. So this has some implication for tools. In particular, tools need to be able to work with every one of these models and every one of the node-level programming models that I just described. So there's quite a few performance analysis challenges for GPU-accelerated supercomputers. We're concerned about understanding the computation performance, where the principal concern is keeping the GPUs busy and computing productively. So we really need extreme scale data parallelism in the applications. There are data movement costs within and between the memory spaces of the CPU and the different GPUs. There's communication between the nodes, there's I/O. And then there's lots of ways where you can hurt your performance. You can have insufficient parallelism in your application, load imbalance, serialization, replicated work, or various kinds of parallel overheads. There's very complex hardware and execution models. So there's multiple compute engines, multiple GPUs and CPUs that have vastly different characteristics and capabilities and performance concerns. There's multiple memory spaces with different performance characteristics, high bandwidth memory and DRAM. And there's complex memory hierarchies on both the CPU and the GPU, which are different. And then finally, with the GPU executions, there's also asynchronous execution in offloading kernels for asynchronous execution. So there are a variety of measurement challenges for tools, constructing tools to measure the performance on GPU-accelerated supercomputers. We've got extreme scale parallelism. And what that means is that if there's any sort of serialization inside our tools, then our tools are going to disrupt the parallel performance. Also, there's multiple measurement modalities and interfaces. So on the CPU, we use asynchronous sampling to measure the performance. There's a callback interface for measuring when GPU operations are launched and sometimes completed. And so that's actually the principal measurement modality for OpenCL. And then there's also GPU event streams that are provided by the NVIDIA and AMD interfaces, where they'll provide a stream of activities indicating kernel launches and timings and other performance information about what's going on the GPU. So one of the key things is that there are frequent GPU kernel launches. And so what that requires is for us to have a very low overhead measurement substrate if we're going to be watching every GPU kernel launch. And I also want to mention that there's an important component that's being provided by the vendors. They're providing these measurement interfaces. And so the tools that we build can only measure what the GPU hardware can monitor. And in particular, support for fine-grained measurement is essential for diagnosing GPU inefficiencies. And so today, NVIDIA is the only one who has support for fine-grained measurement of GPUs. So there's also a collection of engineering challenges for developing performance tools for complex applications that are part of the Exascale computing project. So there's the composition of programming models, the composition of the node-level programming model, and the global programming model is the most notable. But then there's also the composition of things like CUDA and OpenMP offloading within the same program. We've seen application binaries from the national labs that exceed 5 gigabytes. And so anything that we do with binaries has to be efficient. There's HPC libraries that intercept system calls like mmap and open and close. And these are libraries like OpenUCX, which is a communications substrate that's used underneath MPI and other things. There's also quirky application characteristics that we have to cope with. So for instance, when monitoring NAMD running on top of Charm++, we found that exit is initiated by a non-initial thread. And that's something that we hadn't really expected. And then working at the national labs on national security applications, they also have some things where they fork non-readable applications. And so we have to be able to cope with the fact that we might not be able to read the application on disk. We might not be able to read its code while it's executing in memory. And yet, the tool still has to survive. So there's also complications with dynamic library loading that acquire implicit locks, provisioning thread local state, which requires implicit locks, forking processes, interactions with the vendor tool substrates, which are creating threads, and callbacks that may happen on various threads. There's interaction between the tools in the software stack, like we're using asynchronous sampling, and so signals are interacting with all of these other capabilities that I've just mentioned, forking and dynamic libraries and implicit locks. And there's a lack of vendor documentation on their tooling, and so they have non-standard GPU binary formats. And so all of these are challenges that we have to deal with in our project. So as Sanjay was talking about, all of the engineering challenges with Charm++, I can totally relate. So a lot of the HPC Toolkit project is sort of careful engineering to be able to monitor large and complex applications. So for GPU performance tools, what has been done in the past are tools that provided a trace view, which are a series of events that happen over time for each process thread and GPU stream, or they provide a profile view, which shows a correlation of performance metrics with program contexts. So there are a number of different tools that have been developed, the GPU vendors. There's NVIDIA's Nsight Systems, Nsight Compute, and NVProf. There's Rock Profiler from AMD and Intel's vTune. There's also some third-party applications that provide some support for monitoring on GPUs. There's Tau and Vampire Trace and ARM Map. So some shortcomings of those tools for analyzing complex GPU-accelerated applications are that they lack a comprehensive profile view to analyze the complex CPU calling contexts in which GPU APIs are invoked, and also understanding the sophisticated GPU calling contexts that arrive out of OpenMP or Cocos or Raja, where there's a significant amount of generated code. So the code that executes looks a lot different from what you've written as an application developer. And so you need to know what's coming out of the Raja or Cocos templates to execute on the GPU. And so at best, existing tools provide only, they attribute runtime cost to a flat profile of functions that are executing on the GPUs. And as you'll see for these template-based programming models, that's not enough. So let me briefly introduce you to the HPC Toolkit performance tools, and I'll give sort of an overview of our sort of CPU-based capabilities to just give you a sense of what the toolkit is like. And then I'll talk about what we've done for extending it for GPUs. So at a high level, HPC Toolkit operates as a first-party tool within an application's address space. It employs binary level measurement and analysis. So we're observing executions of fully optimized dynamically linked or statically linked parallel applications. It supports multilingual codes with external binary-only libraries with compositions of multiple programming models. On the CPU, we're collecting asynchronous samples, which is an effective measurement modality because it has controllable overhead. It minimizes error and avoids blind spots where we can't observe libraries because there's no instrumentation. Using sampling, you can observe everything. It also enables efficient data collection for large-scale parallelism. So for GPUs, we've extended this to use some GPU performance measurement APIs that are provided by the vendors. So there's callbacks to monitor launch and completion of GPU operations. NVIDIA and AMD provide these activity API interfaces that provide information about asynchronous operations that are executing on GPU devices. And NVIDIA supports PC sampling for fine-grained measurement at the instruction level, and Intel provides GTPin for instrumentation of GPU binaries also for fine-grained measurement. So what HPC Toolkit does is it associates metrics with both static and dynamic context, so loop nests, procedures, inline code, and calling context on both the CPU and the GPU. And so I'll get back to the GPU calling context in a few minutes. So our tool enables you to specify and compute derived CPU and GPU performance metrics of your choosing. And so diagnosis often requires collecting more than one species of metric and then computing equations based on that combine these metrics to gain some insights. So things like GPU utilization. And then finally, the tool supports some top-down performance analysis. So you can identify costs of interest and then drill down to the causes, moving up and down call chains or looking at things over time. So I'll start by introducing the overall workflow for HPC Toolkit that we developed for monitoring on CPUs. And shockingly, the workflow really hasn't changed very much for working with GPUs as well. And so while the workflow is very similar, in fact, internally, the tools have changed drastically. So what we start with is you compile and link an application program as you normally do and produce an optimized binary. And there's nothing special that's needed. You don't have to change your make files. The only thing that can be helpful is if you're compiling with optimization and you don't add a -G, then we can collect information at the routine level, but we can't map it back to individual source lines. The only way you get line level information out of the compilers is to add some kind of -G option. Sometimes the compilers will have a different option like -G opt that says, I want line map information for optimized code. So you compile your program the way you normally do, and then you launch your application. For dynamically linked applications, you launch it with our script, HPC run. And what that does is it collects statistical call path profiles of events of interest on the CPU. And I'll talk about GPUs later. And then where necessary, we're intercepting interfaces for control and measurement. So for instance, we'll intercept interfaces for thread creation and destruction and process exit and whatnot, just so that we can control things. And then we also have to make sure that we maintain control over signal handling and we understand what the application program is doing, and we interpose ourselves between the application and the underlying system. So when we're measuring on the CPU, we're collecting call path profiles. And so what happens is we get an asynchronous sample saying that, say, a timer has gone off, and we'll find that we're at a particular instruction in some routine C, and then we unwind the call stack to find that we were called from B, called from A, called from main. And so from one asynchronous sample, we'll collect a call path that says sort of where the cost was incurred. So the cost might represent time, or it might represent some other costs such as cache misses or instructions. And so then as the application runs over time, we'll take these individual call paths and we'll knit them into a calling context tree. So conceptually, there's sort of main at the top, and a subtree in this might represent, say, an initialization routine and a solve routine and some post-processing routine. And the important thing is that measurement of this is proportional to the sampling frequency, not the call frequency. It's proportional to the sampling frequency and the depth of the call stacks. And so what we're collecting here is a tree that has metric counts that are attributed to the nodes. So it's basically a tree with weights. So then to interpret this data that we collect at runtime, we perform binary analysis offline of an application binary. So we extract information about the line map and the debugging information that's been recorded by the compiler from the executables. And then we also parse and analyze the machine code to recover the control flow graph and recover loop nests from the control flow graph. And we extract these loop nests and identify inline procedures, and then assemble a source level program structure file that maps all of the machine code back to the source code. So to do this, we use the Ntimes toolkit from the University of Wisconsin. We've been working very closely with the Ntimes team, and so we use this instruction API and parse API, which parses application binaries. The SymTab API will read all of the symbol information that's recorded from the compiler, and then the data flow API enables us to do things like program slicing and understand where say, if I'm looking at, say, a register, I can look back in the control flow and find out who defined it or who loaded it. So this works for a number of CPU architectures, and we've been working with the Ntimes team to extend it to support analysis of GPU binaries as well. And so it has reasonably complete functionality for parsing GPU binaries for AMD GPUs using the Vega instruction set. And it has some lightweight support that we use to work with CUDA and Intel GPU binaries, but a lot of the information we're collecting from the outside and sort of putting it into Ntimes for further analysis for instance, analysis of loop nests. So then the rest of the workflow, we take these call path profiles, we combine them with the program structure information, and correlate and combine multiple profiles for multiple threads, multiple processes, multiple executions. And we take all of the measurement data and we correlate it with the static program structure, things like procedures and files, and the dynamic program structure like call chains. And then finally, we assemble information for presentation. And so we have two user interfaces, one that provides a code-centric view and one that provides a time-centric view, and that allows you to explore the evolution of behavior over time. So here's our code-centric view with HPC Viewer. So this was originally developed for analyzing sequential code, but for parallel code, what we found is often most useful is to basically sum over all of the threads and over all of the processes and associate the performance data with the code, because if you're having performance problems, you need to go change the code. And so you need to understand how the performance information is associated with the code. So in this view, we have a source pane at the top, a navigation pane, and a metric pane. And then we have a couple of things for view control. So you can see sort of a top-down view of call stacks, a bottom-up view of call stacks, and a flat view that just shows how costs are attributed to procedures. There's a couple of things for controlling metric display. And so the highlight really is that we have these very detailed calling contexts that we use to attribute program performance. So we get to see function calls in full context. We see information about inline procedures, inline templates, outlined OpenMP loops, and sequential loops. And so the things that are shown in blue are what we actually measured at runtime. And then all of the other information about inline procedures, inline templates, outlined OpenMP loops, and sequential loops is all information that we gather with our binary analysis and overlay on top of our dynamic measurements. So in a profile view, we compress out the time dimension. And so the profile view may often tell you that there's a problem and it's at a particular routine, and you won't understand how that problem arose. So for instance, if there's some sort of load imbalance, and you can see that there's a load imbalance because different processes or threads are spending a different amount of time in there. But if we want to understand how that load imbalance arose, we have to see a trace view, how the program evolved over time. So I mentioned how we're doing this call stack sampling. So to trace programs, what we do is, instead of combining everything together in a calling context tree, what we can do is collect a trace of these call chains over time. So we're collecting a trace of call path samples. And so here, this is showing a sequence of call path samples for an individual thread, and then for each thread in the application. And then what we can do is as we view it, we can view it with this visibility plane that we lift. And so up at the top level, everybody's in main. And then if we lower it, then we might see that over time, that in the early part of the application, you're in some initialization phase. And then in the middle, there's a solve phase. And at the end, there's some sort of post-processing phase. So here's the time view that we get out with our HPC trace viewer. And so what we can see here is we've got ranks and threads on the vertical axis, and we have time on the horizontal axis. And so we have a timeline for every thread and process here to the limits of the number of pixels we have in our display. And so here there's a cursor at a particular point at 77 seconds into the execution, and it is on rank 15, thread 30, and we get to see a complete call stack. Now, you might think that it's expensive to collect all this stuff. Actually, to collect call stacks at runtime, it costs us 12 bytes. We collect the calling context tree, and then for these traces, all we're recording is saying I was at node 56 in the context tree at time t. And then node 56 implies a complete calling context by the path to root in the calling context tree. And so we're able to overlay all that after the execution. So another view that we get with HPC Trace Viewer is there's a summary view in the bottom, where essentially we've taken like a histogram of the activity that is shown in the trace view. I forgot to mention that every color in here represents a different procedure that is active. And so what we're showing here is not a key. This is a call stack for the point that's marked by the cursor. And so I can stick the cursor at each of these things to identify what the different colors are that are active over time. And then in this histogram-like view at the bottom, this is like what projections gives you. It shows you the breakdown of how many threads or processes are executing any one of these activities at any point in time. And there's a statistics display that you can use to find out that information. So I can zoom in on a particular window over time and look at the breakdown of what costs are incurred within that time window. For instance, if there's time spent at OpenMP barriers or locks or whatever. Okay, so now on to, now that I've briefly described what HPCToolkit does, let me briefly dive into some of the capabilities for monitoring the performance of GPU-accelerated programs with HPCToolkit. So HPCToolkit supports monitoring GPU-accelerated computations on NVIDIA, AMD, and Intel GPUs. On NVIDIA GPUs, we're using their CUDA monitoring library. We're also using NVIDIA's Sanitizer library. AMD provides this rock tracer infrastructure for monitoring activities on AMD GPUs. And then Intel has two substrates. They have an OpenCL substrate. Their programming model, the native programming model is data parallel C++, and you can compile that to use either the OpenCL substrate or their emerging level 0 substrate. The level 0 support is still a work in progress, and so OpenCL is the more stable opportunity, more stable runtime system at this time. And then we can also monitor OpenMP offloaded to devices. And so here it doesn't really matter what device it is, because we're using this OpenMP tools interface, which is designed to be as part of the OpenMP standard. So what's new in HPCToolkit support for GPU accelerated codes? Well, one thing it does is it unwinds the CPU call stack to identify the CPU calling context where every GPU kernel is invoked. It also internally employs some wait-free data structures for inter-thread communication. So one of the concerns we had was that if we have multiple threads inside the application that are coordinating the monitoring of GPU activities, we didn't want threads to wait for one another. Otherwise, we would have we would introduce overhead in the execution. So I'll describe a little bit more about that in a minute. We also employ binary analysis of GPU code to be able to attribute fine-grained performance measurements to functions, inline functions, templates, loops, and statements that are running in code on the GPU. And we have binary analysis capabilities for NVIDIA binaries, Intel GPU binaries, and AMD GPU binaries. And this was built in conjunction with folks at the University of Wisconsin. We use a novel technique to reconstruct approximate GPU calling contexts on the GPU to be able to understand the computations in detail. So for the exascale computing project, there were some concerns that at places like Lawrence Livermore, they've built an application called Mercury that does quantum Monte Carlo simulations. And so inside the GPU kernel, the Mercury actually executes about 100,000 lines of code. And so if you tell them that the kernel is slow, that's really not good enough. You have to have sort of fine-grained understanding of what's going on in there. And so as I'll show you, these GPU calling contexts are actually pretty useful. So on NVIDIA GPUs, we're using PC sampling to collect measurements of the activity on the GPU. And that gives us information about instruction stalls. And so we can find that we're stalled waiting for data from memory. We're waiting for a result from a previous computation. We're overutilizing the memory pipeline. And so there's no more slots to issue memory operations, and many, many more things. So there's about a dozen different stall conditions that we can monitor on NVIDIA GPUs using PC sampling. And then finally, our tools provide support for scalable analysis of sparse representations of performance measurements. And so one of the things that's of concern is if we're collecting a lot of performance data, we need to be able to aggregate it. And if we're going to do this at large scale for full machines, then we better be doing this in parallel. So our Our workflow for GPUs is quite similar. You can see this looks a lot like our CPU workflow. So we have our optimized binary and we run it using HPC run, and that reports profile files, and it also can collect trace files. In addition, as the GPU binary runs, or as the accelerated binary runs, we collect information about the GPU binaries that were employed by the CPU. So every time a GPU binary gets launched, there are interfaces inside the NVIDIA, Intel, and AMD runtimes for figuring out what GPU binaries were launched. So we will record the GPU binaries, or we will record pointers to the GPU binaries as the application runs. And then instead of just analyzing the CPU binary with HPC struct, we'll also analyze the GPU binaries as well to recover information about loopness and inline code and whatnot for the code that's executing on the GPUs. And so we'll take the program structure information from the CPU binary and all the GPU binaries and combine it with the profiles and traces the same way that we did before with our HPC Prof and our scalable HPC Prof MPI tools. HPC Prof MPI is just an MPI program for digesting profile information faster. So at runtime, what we're doing is, I showed you the calling context trees that we had before. So we have the CPU calling context tree. And then at the point where kernels get launched, we associate the CPU calling context with the context of the kernel that gets launched. And then using NVIDIA's APIs, we can collect information about the kernels, such as how much time it ran for, the register usage, the shared memory usage, and things like that. We can also get information about the sampling frequency and the clock frequency that was used when the kernel was run. And then we can use PC sampling to collect information about individual instructions that are inside the kernel. And for each of these individual instructions, we can collect instruction counts and stalls, and like total stalls, or stalls for memory, or stalls for synchronization, or stalls for waiting for dependent instructions, things like that. So what we have is a calling context tree, and we have a sparse set of metrics. And so some of the nodes have CPU metrics associated with them, and other nodes have GPU metrics associated with them. But there's like about 100 GPU metrics that we collect. And we don't want to associate those 100 metrics with every node in the calling context tree on the CPU. And so we are able to represent these in a sparse form, so that our storage is only representing the GPU metrics associated with the GPU portions of the code. So as a preview of what we're able to do, this shows that we have this calling context. This is our HPC viewer user interface. We have the calling context on the CPU, and then we see that a GPU kernel gets launched, and we can see a mangled name for the GPU kernel. So this is from the AMRX AMR solver that's being developed at Lawrence Berkeley Labs. And then inside that, we can see loops and inline code and actually function calls. So we have some fine-grained metrics like GPU instructions. We have coarse-grained metrics like GPU kernel execution time that are reported back to the kernel level in the call stack. We also have derived metrics about GPU utilization for within this context. So let me tell you a little bit about how we go about collecting and assembling this. So when doing performance measurement on the GPUs, there's three categories of threads. There's the application threads, there's a monitoring thread, there's one per process. And so this is monitoring GPU events and collecting GPU measurements. And so for NVIDIA GPUs and AMD GPUs, these monitoring threads are provided by the CUDA and ROC tracer tools. And we also have some threads that we create inside our tool to support tracing for GPU execution streams. So whenever we turn on tracing, a CPU thread records its own traces, but we actually have to have some CPU threads that are acting as proxies for the GPUs and recording the GPU streams. So there's some interactions between the threads. We're correlating activities that are launched by the application threads with kernels that are observed by the monitoring thread. So we need to attribute measurements that are collected by the monitoring thread and send them back to the application thread to be logged in its calling context tree. And then finally, we need to record traces where the monitoring thread will gather information out of this stream of activities that's coming off the GPU measured by NVIDIA's CUPTI or AMD's ROC tracer. And we want to put out a tracing timeline. And so the monitoring thread has to communicate with our tracing threads. So as I mentioned earlier, one of the concerns is that the threads might get stuck waiting for one another. And so what we did is we built some efficient communication mechanisms for that. So this is sort of an overall layout of our runtime monitoring infrastructure. And so this is specific for OpenCL. The details are a little bit different for working with AMD and NVIDIA infrastructures. In fact, they're simpler. So on what happens is the CPUs are going to launch work on the GPUs. And when they launch work, there's a GPU API callback that says that a kernel is being launched or a memory copy is being launched. Now, who receives these callbacks actually depends upon whether they're synchronous or asynchronous activities. So if I perform a synchronous memory copy, then the thread that launches it will probably get the callback. If I perform an asynchronous kernel operation, then in fact, someone else might get the callbacks for the launch and the completion. And so we have to deal with the fact that the thread that actually needs to log the performance information that says I launched this on a GPU is not necessarily the thread that gets the information about it in a callback that says that I launched a kernel that took so long. So what we do is we take all these measurements and we put them into these channels that are sending all of it to a monitoring thread of our design. And so these operation channels, the monitoring thread is going to multiplex and inspect all the operations that are being launched, and it processes them and then sends information back to the application threads for them to log in their calling context trees. And so we have stuff streaming into our monitoring thread and stuff streaming out back to the application threads in this way, and then stuff streaming out to these trace channels to be logged in trace files to record the activity. So a key component to make all this efficient are these channels. So what we developed is a set of wait-free data structures, of wait-free channels for inter-thread transfer of measurement data. And so the core component of this is a unidirectional wait-free channel between a pair of threads. So for those of you who are not familiar with this terminology, we can either coordinate using shared data structures with mutual exclusion. And so while I'm operating on the data, nobody else can. Or we can use so-called lock-free data structures where there are no locks involved, but there might be spin waiting while somebody else is working on the data structure. So I can try to do an operation on the data structure and then fail. Wait-free is actually a very strong performance condition. What it says is that any operation that I try on a data structure is guaranteed to complete in bounded time. And so what we built is a wait-free channel between a pair of threads that's implemented by a pair of stacks, one that's private and one that's shared. And so what we do is when we're trying to send information from one thread to another, whoever is providing the information is performing a push on one of these stacks. So it's pushing an item on a shared stack, and it does the push with a compare and swap. And then who's ever on the consumer side of the channel can steal the contents of this shared stack, and the shared stack may contain a whole bunch of items that have been pushed on it already. So it steals the whole contents and then pushes that contents onto a private stack. And then the consumer continues to pop elements from the private stack until the private stack is empty, and then it goes back and it steals the rest of the shared stack from the producer. So this is wait-free because the push can fail at most once when a concurrent steal is stealing the contents of the shared stack. Because a steal is going to perform a swap and say, I'm going to swap this top of stack pointer with a null. Once it's been set to null, then no other steal operations are going to change the state. And so a compare and swap that's trying to swap from null to push something on is going to succeed. So a compare and swap can only fail once. And a swap operation will in fact never fail. And so there's no spin waiting. There's in fact, you can end up having to retry a compare and swap exactly once. And so this forms a wait-free one-directional channel. And then we have a bidirectional channel that's a pair of these stacks. And so we're sending records down the channel. and then whoever consumes them and consumes the information sends the data objects back to us for them to be recycled and refilled. So in order to coordinate GPU, in order to correlate the GPU API invocations with the CPU calling context, we're going to unwind the call stack at every API invocation, which is like every kernel launch, memory copy, or synchronization. So our initial approach was to identify the function enclosing each call site in the call stack using a global shared map. The problem was that that applications have very deep call stacks on a large code base. So we work with a couple of DOE codes, one called Nix that has 60 layers in the call stack. Another one, Lagos, has 40 layers in the call stack. And then there's lots and lots of calls. And so using this global shared map was actually costly. So it's a mutable shared map where we're keeping information about where functions are in the address space, the range of functions. So what we did is to facilitate unwinding, we would end up both memoizing call path prefixes so that we didn't have to unwind every step in the call stack. Whenever we got to a common prefix, we could identify that we knew where we were, and then we didn't have to unwind the rest of the stack because the rest of the unwind was known. We avoided access to this mutable concurrent data structure by caching unwind recipes in a thread private hash table. And then we avoided duplicate unwinds. So the CUDA driver APIs and the runtime APIs end up both getting invoked for the same kernel launches. And so we unwind out of only one of them. So what we found was that it was important to have GPU calling context to understand performance. And so GPU code that is derived from these template-based programming models is very complicated. And the NVIDIA GPUs can collect flat PC samples that can provide us some detailed information about what's going on inside the GPU kernels. But flat profiles for instantiations of complex C++ templates are inscrutable. So take a look at this. This is code from the Raja template-based programming model. And this is code that got generated for a dot product. And so the implementation of the dot product on the GPU, there's actually 25 routines that are components of the implementation. And if you see a flat profile, you're just left with this inscrutable set of instantiated templates without really any understanding of how they compose with one another. So what we do actually is we reconstruct approximate GPU calling contexts. We reconstruct the call graph from the machine code, and we infer from the call sites. We identify the call sites in the machine code, and we use PC sampling to recover call graphs. And so what we're able to do is to reconstruct something that looks like this. And so here, a dot product, well, we see that there's a for all, and then it's calling a dot routine, and then it's performing a sum reduction of a reduce operation, calling reduce data, and then we see some inline code and loops all the way down to the routines at the leaves. And so this is actually for the same data, and I would argue that this view is a lot more comprehensible than the previous view. It helps you understand what this complex template-based code is doing on the GPU. So how do we do these approximate reconstructions of the calling context trees on the GPU? Well, unwinding call stacks on the GPU is complicated, and CUPTI doesn't provide an unwinding API. So the challenges are that GPU functions can be invoked from different call sites, and we need to understand how to attribute cost to each call site. So the solution is that we reconstruct a GPU calling context tree from flat instruction samples and a static GPU call graph. So initially what we do is we inspect the machine code. So for NVIDIA GPUs, we actually have to invoke the NV-DisASM tool that NVIDIA provides to recover the machine code. And so we analyze the machine code and we identify the call instructions. And so from the call instructions, we can build a static call graph. And so that tells us what calls what. But we want to understand what function calls actually got invoked, like how many calls were invoked at every call site. And so we're using PC sampling to measure the execution on the GPUs. And so what we're doing is we use the samples of call instructions as a proxy for how many calls get done from each call site. And so what we do in our static call graph is we label the edges in the call graph with the call counts, the sample counts for each call instruction that were observed. And so here we have a pair of mutually recursive routines that are a cycle in the call graph. So we take our information from PC sampling, and then we do some propagation, because it may be the case that we found ourselves in a routine or in something that routine called, and we don't know, we never sampled the call instruction for this. And so we know that we were in there, and there's only one way to get here. So we propagate we propagate a sample up to say we know that there was a call. And so what we do is we propagate activity up to a caller until at least one of the call edges has samples on it. And so so we start with our initial call graph or our initial static call graph with weights on the edges, do a little bit of data flow analysis on it, and then we identify strongly connected components using Target's algorithm. And then we remove the edges within the strongly connected component. And now, instead of having calls to individual procedures, we just indicate that there are calls to the strongly connected component. And then we take the costs that are attributed to each of the procedures. So like costs that are attributed to the strongly connected component, we see that there were 2 calls from one location and 6 calls from the other. And so what we do is we make an assumption like gprof that every function call has equal cost, and we apportion the costs among each function among its call sites according to the ratio of the calls. And so this is the way that we reconstruct our approximation of calling context trees on the GPUs. And so we've done some comparisons of our reconstructions with some reconstructions that we've done using instrumentation with NVIDIA's NVBit. And we found that, in fact, that they're very accurate, and they also appear to be useful in practice. So here's an example. So this is the ECP Quicksilver application. So this is a proxy application for the Livermore's Mercury code with this quantum Monte Carlo code that I mentioned earlier. And so here's what we see inside the kernel. So we see this GPU kernel cycle tracking kernel was launched, and then it calls a function cycle tracking guts, which has a loop inside it, which calls collision event, which has a couple loop inside that, which calls macroscopic cross section. And then there's some inline code there for that calls nuclear get reaction cross section, and then it gets the cross section data out of a vector. And so we argue that this is like a very useful way to look at the GPU executions, rather than just look at, say, flat profiles with costs next to every source line, without any understanding of how you got to the individual source lines. So we also have support for OpenMP offloading. And so this is something from the QMC pack. Mini QMC is a code that was developed to test as a proxy application for QMC. And so we can see here is we've recovered information about offloaded OpenMP code. And so then it goes through a series of template instantiations, and then we get a kernel that's offloaded on the GPU, and we get to associate the cost back with the OpenMP outline function in the full program context. We can measure Raja and Coco's template-based programming models, and we can see the template instantiation and see the template generated code and relate it all the way back to the context. So if the names of the functions are 2,000, 4,000 characters long, you really can't tell exactly what they are just by looking at them. What's important is you go back to the calling context where the code was instantiated, and then you know exactly what operation that you're trying to perform, and that's the routine that's doing it and the cost that was incurred. So we have some support for deriving GPU metrics. So I thought I'd mention that we measured GPU-accelerated NAMD using Charm++. And so we can identify that there's a costly line in context. So this is assigning the electrical energy calculation. So we can see, I marked it with red dot where it is in both the navigation pane and in the source pane. And then we can see, using the PC sampling, we can see that that there's a significant amount of stalls here, about like 1/3 of the time that's, or 1/3 of the instructions here stalled. And that the reason why we had stalls is because they were stalls on waiting for memory. And so in fact, this is accessing E of I, and so E of I is defined up here. And so this is stall waiting for the load from texture memory. We can see that there's full utilization of the GPU by the kernel, and we can also get information from NVIDIA's CUDA API showing us how many registers and how many threads per block, and how many blocks, and the GPU occupancy. So while NVIDIA's tools provide information like this, and also the stall information, they don't provide everything in the calling context. And as it just showing you that I think the calling contexts are really important for understanding these big codes. We also can trace these large-scale GPU executions. And so this is a trace of this cosmological code called NIX that's using an AMR solver. And so we're seeing both CPU and GPU trace lines in this view. If we zoom in on a small part of the execution, in fact, the CPU trace lines sort of look like this, and then all of this is activity on the GPU. So it lets you see some of the structure of what's going on. The green here, I think, is actually synchronization operations that are happening on the GPU. And so by looking at these traces, you can uncover synchronization issues and imbalance issues and places where the GPU is idle, where nothing is getting offloaded to it. So I'm running a little tight on time, so I'm just going to go through this very briefly. So one of the things that we are working on is support for scalable analysis of performance data. And so we collect these profiles for every thread and GPU stream in the execution, and then we need to unify them all together to get a unified set of call stacks across all of the threads. And then we produce the information in a sparse form where we have one set of metrics where we're indexing them by profile, like by per thread. And then for every calling context, we have a variable set of metrics. So we have a sparse set of metrics as indicated by this sort of sparse pane. So that's one form when we want to access things by thread. Also, sometimes it's useful to look and see if everybody is executing a balanced amount of work in a particular context. And so we want to access things by context. So we have another sparse form where it's indexed by context ID. And so both of these are four-dimensional representations where we're indexing by in a sparse form. And so they're generalizations of like a compressed sparse row format. So one of the things that we did is we looked at, we're using both MPI and OpenMP. And so the question was, well, what's better to use if we have the option? So within a node, should we use more MPI ranks or more OpenMP ranks? So this is comparing the scaling by adding more MPI ranks within a node and adding more threads in a node. So these were done on a Knights Landing processor. And so it supports up to 256 threads. And what we saw was that we were getting performance improvements out to 128 threads, whereas the performance started to tail off by adding additional MPI ranks over 1 per core. So this is 1 per core and 2 per core. So we're seeing some benefits in our threading model using the hyperthreading in the KNL processor. So here we're looking at 64 cores. Should we use them as threads or ranks? And so we find is where we're looking at one rank with, where we're using all ranks, and then out here we're using all threads, and we find that the all threads is much faster within a node than ranks, and so it's about twice as fast. So we prefer using threads rather than ranks to analyze the performance data. And then looking at the benefits of sparsity, so we found that I mentioned that for the GPU kernels, we can collect as many as 100 metrics. And so if we don't exploit the sparsity and only represent the GPU metrics for code that's running on the GPU, instead of representing GPU metrics everywhere, in fact, we could save a factor of 200 to 300 in the resulting outputs by exploiting sparsity. So this is showing that this is actually showing an execution using our trace view of our scalable analysis. So this is analyzing 64K profiles from a CPU base called AMG 2006. And so while the input data is small, this is only about 5 gigabytes of profiles, we're able to analyze 64K profiles and correlate them all with source code and whatnot in 184 seconds across 8 MPI ranks with 128 threads per rank. And so the blue here indicates some load imbalance, but all the rest of it is very highly threaded and very efficient. And we're not spending our time in locks. There's like almost no locking in this program at all. So, so what we found is that as we scale, we actually get very good scaling in the performance as we add, as we use additional profiles. Then we find that that our execution time is linear in the number of profiles, and that adding more threads reduces the execution time. So this is actually looking at analyzing, out here is looking at analyzing 200K profiles. And so, so actually we're pretty confident that we could do with even just on 8 nodes of theta, we expect that we could do 1 million profiles in a half hour using larger resources. In fact, you can go faster than that. So finally, some status and some final remarks. So for the different GPUs, we're supporting NVIDIA, Intel, and AMD GPUs. The fine-grained measurement is supported by PC sampling on NVIDIA GPUs. We're using GT-Pin for instrumentation on Intel, and there's no fine-grained measurement capabilities for AMD yet. So some ongoing work, we're building a GPU performance advisor tool that attributes instruction stalls with backward slicing, analyzes code, and offers some advice about program improvements. We have a new user interface, and we're looking at performance analysis of machine learning networks. So a couple of final remarks. It's nice to work with the national labs that have early involvement in a big procurement. It amplifies our ability to affect the vendor software and hardware in the near term. And there's a lot of software development challenges. Trying to develop tools for 3 GPU software stacks at the same time is kind of ridiculous, but that's what the whole Exascale program is about. So sorry I'm running a little bit late, but I'd be happy to take any questions that you might have.
Certainly, thank you very much. We are going to be okay going a few minutes over. So so anyone has a question that's already, we just put the Google Doc out again, but since there's no question there, go ahead and ask question. It's okay. If 2 people speak over each other, that's not a problem. We'll resolve it. I had a question, but I kind of have to retrieve it. Can you go back to your slide 32? 31, maybe.
Sure.
I had a broad question and a narrow question. So, I see. Calling context, maybe I think I remember this now. So maybe it is the 30 or 31. The point is, I had forever, I haven't paid, I must admit, that much attention to it, but all methods that try to do sampling seem to be inaccurate when the grain size is small, when their durations are small. This is noticeable in GPROF. You probably do better, I don't know. But the other side of that coin is that I feel like there is no need for those because the overhead for timer calls has gone so much lower, or at least it had. It's just a register lookup that every entry exit can be actually traced. So, and if you don't want to store it, you can increment some counters or whatever. What do you think? I mean, is there a need for sampling still?
So I think that so if you're doing tracing with timer calls, are you talking about just tracing something like GPU API invocations, or are you talking about tracing every function entry and exit? Every function entry and exit, yeah. So actually, there were some experiments that were done by the Tau team on tracing at that sort of granularity. And so I remember when they were doing this for this quantum chemistry framework called MADNESS that uses these template-based programming models. And so what they would do is they would process the source code, and then they would add like enter exit things to every template that you were instantiating along the way. And so what would happen then is that both, like adding these timer calls, both could disturb the template instantiation. And so what they ended up with was an overhead of a factor of 30 when for this very complicated code. And so a lot of that overhead came from tracing very fine-grained things like lock acquisitions that were just minuscule. Okay, and so what they said is, well, so we'll use this technique called throttling, where for very frequently called procedures, we just won't trace them. They're very frequently called and they're short. Yeah. Well, once you applied that throttling, then they completely missed the fact that there was actually lock contention and that was a problem, because the cost of tracing all of these very fine-grained routines for locking caused them to say, oh, we need to use throttling in order to bring our overhead down. But if you bring the overhead down, then you completely miss the performance bottleneck. So I would argue that with sampling, that we can see those kinds of things and get all of this detail throughout templates without actually any cost by overlaying all the information after the fact. So we found that sampling is actually very useful, both at like, not just at the routine level, but attributing costs within individual routines and within particular contexts. And so I don't say this as someone who's just sort of like trying to sell an idea. We use this all the time, okay? So for instance, when we were developing our scalable performance analysis, we are using our tools to understand the inefficiencies in it and then correcting the algorithms where we're spending too much time in particular places. We're noticing lock overhead and refactoring data structures and things like that. And so the sampling is just incredibly helpful to get that very fine-grained detail. And on the GPUs, the sampling gives you instruction level detail. And you can't get that by just using timers.
Yeah, but I guess you're right. I have to look at it again to understand it. But you are saying somehow, even with sampling, I would have argued that sampling would miss those fine-grained details too, because it's just, you won't get into those situations often enough. But you somehow seem to think that's not the case.
If you collect enough samples, so you don't actually have to sample at a very high rate, but if you collect enough samples because the application runs for a period of time, then that gives you very fine-grained detail inside the application and allows you to make very, very detailed analysis decisions.
Yep. Okay, that makes sense. Yeah. Okay. Another question? There's a question from Nils. Nils, you go ahead and ask the question unless you want me to read.
Yeah, so this is really nice, and I really like the sort of the views that the view parts that you've adopted from projections. I always found them useful. So I sort of have two separate questions. A few years ago, we tried HPCToolkit, and we ran into some issues with LD open and loading churn++ and OpenBLAS when OpenBLAS was built with threads, even if we disabled threading and this kind of thing. General question, has there been work done on sort of improving HPCToolkit and churn++ interoperability and this kind of thing since then? I think this was
there has been a lot. So you notice that there's this page of war stories. Okay?
Yeah.
And so OpenBLAS creates threads inside its init constructor. And then if we fork off a helper process, then it invokes @fork handlers that trigger thread destructors, and there's chaos. Okay.
Yeah. Okay.
And so we've addressed all of these things. So we don't fork, we use clones so the @fork things don't get invoked. We are very careful about now tracking dynamic library opens differently using this LD audit layer. And so that's something actually the best support for churn++ is actually in our develop branch right now, which you can build out of spec. But what I would say is that all of this is a work in progress. As you can see, we're both hardening it for these complex applications and for 3 GPUs and scaling all at the same time. Okay, right. So what I would say is that all of these improvements are coming to our master branch as soon as we can integrate them, which is going to be over the next month and a half. Okay.
Oh, that's awesome. That's a really good timescale for us, actually.
Yeah, that's great to hear. Projections that Nils mentioned we are very used to it. We really like it. I really like it, as my students know. But it's a tool we designed in 1994, and it's been continued to improve. It's based on basically a tracing framework, and the sampling and call stack issues have been ignored. And it will be great to be able to use those two in conjunction. But we find projections useful for scaling type of analysis. But these other issues will be very good to have that as a complementary, at least, or if not exclusive tool. So
right. So projections is operating at the level of individual chars, correct?
It knows about chars. I don't know what you mean by operating at. It knows about.
What I mean is the instrumentation is like not at like the loop level or whatever. It's at this higher level.
Method
right?
invocation.
So,
yeah.
And so what we get is all of the detail for all of the code that's executing inside.
Yep. Right. That's correct. Yeah.
So like at the high level, the projections level view can tell you about scaling, and it can tell you that you're not doing enough of this or you don't have enough of that parallelism, but it can't tell you internally why something is inefficient. Right. That's what we can do.
Yeah.
Okay.
Excellent. Okay.
Right. That was basically, well, so first, thank you so much for dealing with all of this nightmare that is, like this OpenBLAS thing. I'm so sorry and thank you. And my second question was,
OpenBLAS is only the half of it. Okay.
Yeah, I'm sure.
The ML frameworks like PyTorch, there's more war stories on there from PyTorch.
Yeah, I'm sure. So yeah, my second question was sort of, if I remember correctly, HPCToolkit does sampling, right?
Yes.
Yeah. All right. Okay. And so that's exactly what you and Sanjay were just talking about. That's something that sort of was the thing that I've been missing with projections. Is I would like to be able to do sampling and so that but have sort of these nice views. So I guess this has turned into less of a question and more of a comment that I'm really looking forward to testing out this new HPCToolkit. That looks
okay.
Really nice.
Well, we would love to work with you. I didn't get a chance to try it out on like a larger NAMD thing on Summit last week when I was looking at NAMD. I could only figure out how to build GPU-accelerated NAMD for a single node, and so that's all I looked at so far. But I saw that there was a paper that was looking at NAMD performance on Summit, and I was very interested in sort of trying it out to see how our GPU-accelerated infrastructure would be able to monitor that.
I mean, just to correct an impression, Nils comes from a cosmology community, and his application is Spectre and Changa. There are these 3 or 4 other highly scaled applications that might be, of course, others too would be, there may be a dozen. So people might be very interested in exploring this, and you might be interested in some of them as at least research-wise or otherwise use cases.
Absolutely.
So,
absolutely. And so if you're interested in exploring something with HPCToolkit with Churn++, if you try it out and have any questions or run into problems, please send a note to our mailing list. I suggest the mailing list rather than me, just because my mailbox is just way too full. And so at least with a mailing list, there are other people on my team who will look at it and make sure that it gets some attention. It'll probably end up on my lap, but someone will say, John, read this email, which is helpful.
Okay, yeah, no, that's perfect. Yeah, so basically we solve hyperbolic partial differential equations using, so it's a grid solver. And so basically we have some very floating point intensive loops and these kinds of things, but then we also have to worry about all of the inter-process communication. And so it seems like HPCToolkit would be able to give us a view of what are we doing bad in terms of the floating point or memory allocations, bad memory accesses, and also be able to give us the view of how bad are we doing on the communication. So thank you.
That's the theory. And then if there are, little interactions like with the software infrastructure, we promise to address them because this is like on our hit list. If we're going to meet the challenges of the DOE ECP project, we have to be able to work with the most complex applications on the planet.
So we are running a little late. David Hardy has a question. I had a question. I probably could postpone my question, but let me ask you briefly, then you can tell me a forward pointer so we don't forget. Is that I was very interested in your stack, what do you call it? The CAS-based one process to process channel. Is that code somewhere I can see?
It is. That is in the HPCToolkit master branch. In something called a bidirectional channel.
Yeah, because that steel process was not clear to me how the steel happens, but I will look at it later on.
There's also an ICS 20 paper that describes our tool and actually has the pseudocode for this and explains it. Okay,
excellent.
That's a good place to look for it.
Okay, will do. Thanks. David Hardy, your question briefly.
My question was already answered. It was just whether or not these tools worked on power, processors. And so for the purpose of, again, profiling NAMD on Summit. So I can certainly help you build a parallel version of NAMD for profiling on Summit too. So yeah.
Absolutely. So that would be a great thing for us to look into together, because I think that if we are not able to deliver insight into what you're doing, then we're doing something wrong. And if we're doing something wrong, then that's a research project for my students. So we'd be happy to work with you on it.
Okay, great. Thanks a lot. That sounds great.
Excellent. All right. Thank you very much. And it was an excellent talk. We went over a bit, but that's okay. Thanks a lot. Hopefully you can stay for a talk or two, but otherwise we'll stay in touch.